So the other night when I was watching Jaren's live feed on Max Egan's flight to Santiago, I got chatting with Bob from Globebusters about the maps. And I threw out my challenge to him, which I've done often to other Flat Earth channels, and that is to show me a map that works. And Flat Earth really doesn't even have an accurate map that they can show anybody. And Bob turned around and threw that right back as the same question, saying, well, show me an accurate globe map. And he mentioned that there are many inaccurate globe maps, and I don't disagree with that. Certainly in the past, the globe wasn't precisely mapped, and going back 300 years, certainly they didn't know anything about the southern hemisphere. But we're now in 2017, and we've got this World Geodetic System WGS-84, which is an incredibly accurate world map. So if anybody asks you to show them an accurate globe map, just steer them in the direction of WGS-84 and ask them to do some research. All you've got to do is just type in WGS-84 in Google and you'll get a whole list of links. Now, what I'm going to do is just talk briefly, and I'll try not to get too technical with it, about how accurate WGS-84 is, and then I'll pause the video and then I'll show you absolute proof that this works in the real world. And firstly, let's just have a look at what this site says. Okay. WGS-84 is standard for GPS. The World Geodetic System WGS-84 is the reference coordinate system used by the Global Positioning System. It comprises of a reference ellipsoid, a standard coordinate system, altitude data, and a GeoID. Similar to the North American datum of 1983, it uses the Earth's center mass as the coordinate origin. The error is believed to be less than 2 centimeters. Okay, so we're talking about an accuracy of 2 centimeters. Now, a couple of other sites, let's look at where they describe what WGS-84 is. It's a geographic coordinate system, which is what WGS-84 falls under. The definition given by ESRI states that a GCS uses a three-dimensional spherical surface to define locations on the Earth. Okay. Basically, a GCS is used to define your real-world points on a three-dimensional digital surface. Examples of this include WGS-84. Okay, and this site, which I'll link to, also has a lot of good information. Okay, what are geographic coordinate systems? A geographic coordinate system uses a three-dimensional spherical surface to define locations on the Earth. Okay. So that's basically what we're looking at there. Now let's just have a look at how accurate it is. If we look at the diameter of the Earth, Google tells us that it's 12.742 million meters in diameter. Okay. Now if we just go through a small piece of logic here, the Earth's diameter is 12,742,000 meters. The accuracy of WGS-84, I've typed that wrong, take that 2 out. Okay, WGS-84 is 2 centimeters. Let's just, for the purpose of this explanation, assume the accuracy is only 1 meter. So we're actually giving it 50 times less accuracy than what it is. So let's just assume the accuracy is only 1 meter. Now 1 divided by 12,742,000 is that number. It's 0 followed by 7 zeros, 78. So if we are going to construct a physical model of the globe that is just 1 meter diameter to this accuracy, okay, the printing of the ink that displays the continent locations on that globe would require an accuracy of 0.078 of a micron. A micron is 1,000th of a millimeter. Okay, so that's just how accurate it is. So basically, if we look at the width of our little mouse, that's about maybe 2 millimeters in diameter. So we're now talking about thousandths of times smaller than that little mouse cursor. That is how accurate we would have to print the continents on a globe if we were constructing a globe of 1 meter diameter to the accuracy of WGS-84. So it's not just an accurate map of the Earth, it's not just an accurate model, it's just an incredibly accurate model that is so accurate we probably couldn't even produce a scale model of it. Okay, we're talking about printing accuracies of 0.078 0.078 of a micron. Okay, now I don't know if that's actually possible, but I think we can all agree that the accuracy is just incredible. Now what I'll do is just see how this actually relates in the real world, because that's the proof, that's the test. You know, it's all good to talk about math in theory and on paper, but the real acid test is to see if this works in the real world, and that's the proof. If it works in the real world, then it's obviously true. So now we're going to take a look at the proof that WGS84 is accurate in the real world, and that's the key. If it's not accurate in the real world, then it's pointless. But if we can prove that it is accurate in the real world, then it's correct, obviously. So let me just look at a couple of flights. I'm going to look at a flight from Sydney to Honolulu, and I'm also going to look at a shorter flight from Tucson in the USA to Los Angeles Airport. But the basic concept of what we're proving here is that GPS is based on WGS84. The flight management system in most aircraft, airliners, corporate jets, is also based on WGS84. Instrument approach charts and runway plates are all based on WGS84. And if you look through Jeppesen documentation, any of the charts that have this latitude and longitude position on the border is actually based on WGS84. Okay, the only airports that are not currently based on WGS84 are some of the smaller airports in China, but the major ones like Beijing and Shanghai, they're certainly all now referenced to WGS84 for use by aircraft. So, how do we prove that it's correct? Well, when I first learned to fly more than 30 years ago and I did my instrument rating, we had to track using ground-based navigation aids. There was things called non-directional beacons and VORs and DME, distance measuring equipment, and we would have to reference those ground-based instruments from the aircraft just to provide tracking information and to go from one beacon to the next as we were tracking across Australia. These days, most of those beacons have been disabled and decommissioned, and navigation is conducted by reference to GPS and by reference to the WGS84 map of the Earth. So essentially, I can take off from Sydney, I can cruise in cloud or above cloud, so I cannot see the ground at all. I can go for 9 hours and arrive at Honolulu. I can then set up for an instrument approach, and the instrument approach can be what's called an RNAV approach, which I'm going to look at shortly. But the RNAV approach is based again on WGS84, the model of WGS84, and it has lateral and vertical positions that we will fly to, and essentially in cloud, if we've got poor visibility, we can fly the RNAV approach right down to 200 feet, and then when we break out of the cloud, we are perfectly aligned with the runway. Okay, so think about that. We've taken off from Sydney, we've flown for 9 hours without seeing anything on the ground. We've tracked through the WGS84 coordinates of an instrument approach, and at 200 feet, when we break out of the cloud, we are perfectly aligned with the runway. Okay, now this happens all over the world. International flights, domestic flights, thousands of flights every day are proving that WGS84 works. So let's just have a little bit more of a look at some of these charts. And what I'm going to do is just go to this flight here. Okay, we've got SkyWest 459, which is scheduled to depart in 45 minutes. Now, let's go down and take a look at his flight plan. Okay, his route is from Tucson via the Burrow 4 standard instrument departure, GBN, Juliet 104, Tango November Papa, and then via the Seaview 2 Star, and that's a standard arrival route. So let's just have a look at that route. Okay, let me have a look at it in a couple of the aviation apps that I've got. I've put Tucson via the Burrow 4, Golf Bravo November, and the route into KLAX. And let's take a look at it. You'll see that by entering the Burrow 4, it's got a track out of Tucson via Burrow, via Splits, Rin, and off via those points. Okay, as we get into Los Angeles, okay, there's Seaview, and the actual approach is all these reference waypoints in advance. It's all based on WGS84. And the thing is, it works. And this aeroplane is going to take off from Tucson in about an hour. And if the clouds were thick and low visibility, it can fly just following this flight path in the GPS, and it will arrive at Los Angeles perfectly aligned with the runway once it flies an instrument approach. So let's just go back to Jefferson. And again, I've put that route in the Jefferson mobile flight deck, and that little pink magenta arrow is just showing my current location in Colorado, USA. But just getting back to this, okay, we'll have a look at the route. There it is again, and I haven't put in the SID or the star, but we can take a look at those over here. So let's go out of Tucson, and let's take a look at the standard instrument departure, SID. Okay, there's the SID. Now if you hit it twice, you'll get the whole list, and I've already selected the Burrow 4 RNAV. Now RNAV means it's referencing GPS. It's relying on WGS84 and nothing else. Okay, and if we have a look at the Burrow 4, it goes off Tucson to Burrow to Splits and then to Rin, just as we looked at before. So the airplane can fly those paths. And remember, it's a three-dimensional path. It's not just lateral. There are three-dimensional requirements, because you'll see there at Rin, the requirement is to be at or above 8,000. At Rosca, you have to be at or above 9,000. And the same thing happens when you're coming into fly and approach. So come back to Los Angeles. Let's look at the star, which is the standard arrival route. And I've already selected the Seaview 2. And there it is. Okay, so it starts at Tango November Papa. It shows you the distances, it shows you the directions. There's a holding pattern if necessary. There's the vertical requirements at 280 knots at 17,000 feet at that waypoint. At Engley, at or above 16,000 feet. So this is how precise the aircraft are flying. Okay, once we get to this point, Seaview, we need to be between 14,000 and 12,000 feet. Okay, so in addition to having lateral navigation requirements, SIDs and stars also have vertical requirements. Now just pause there, and then we'll get into the next one, which is just talking a little bit more about the actual approach itself. So at the completion of a star, a standard arrival route, you generally commence an instrument approach. Now, again, when I was first learning to fly, we only had ground-based aids such as the ILS, which is an instrument landing system, and they are still frequently used, and we still use them quite a lot. But we now also have approaches that are purely based on GPS, and one of the most accurate is called an LPV approach. It's localizer performance with vertical guidance, and it's the highest precision GPS aviation instrument approach currently available. Okay. Now you can actually get more accurate ones, but then you need specialised aircrew training and assessment, which a lot of corporate aircraft don't particularly have, but certainly the airlines do. Anyway, let's just focus on LPV, and I've just pulled up the approach chart for Oklahoma City, and this is the instrument approach. It's not referencing anything on the ground. It's purely based on GPS position and WGS84, and once again, it's got lateral and vertical requirements, okay? And the LPV minima is 1487 feet, which is actually 200 feet above the ground. So again, if we were flying to Oklahoma City in snow, at night, bad weather, poor visibility, we just fly this approach and we follow the lateral and vertical path, and we're going to break out of the cloud at 200 feet, perfectly aligned with the runway, okay? Now that means WGS84 is working in the real world, because if it wasn't working, we would not be lined up perfectly with the runway when we break out on our approach. So this is the fact that WGS84 is working. Aircraft are using it every day to navigate accurately around the world in poor visibility, and breaking visual on a GPS approach, an RNAV style approach, exactly in line with the runway. So now let's take a look at Honolulu as well. So again, looking at the flight from Sydney to Honolulu, remember I mentioned we could take off from Sydney, fly above or in cloud for 9 hours, and then arrive at Honolulu. Now let's just go back to Jefferson flight deck. we're going to have a look at some of the departure routes out of Sydney. And this is a common one that we fly when we're heading off overseas. We're in Sydney, we'll go to the standard instrument departure. And the one I've selected is the, let's have a look. It's actually the Kevin 5, okay? That's the Kevin 5 departure from Sydney. And we take off from 16 left. 500 feet we turn, we follow that path. At Kevin, we then assume our route, and that's when we would commence our tracking up to Honolulu, okay? But it's all based on WGS-84. The directions and any altitude requirements are all based. So there we go, on passing 10,000 feet, turn left and track up to Entra. Now, usually at that point, they'll just give us a vector to our first waypoint en route, and we'll be on our way. But if we come to Honolulu, we're going to look at the standard arrival route, and the common one that we get coming from Australia is the Parker 4, and that's what it looks like. Okay, so we come in via one of these waypoints, usually Carp, and we then fly that track to a Parker, and from that point we can expect radar vectors, or we will actually be vectored directly to the initial approach fix for the approach. And let's just pick one of them. Now again, I've selected the RNAV, which is purely GPS based on WGS-84, because we know that because it's got the latitude longitude lines on the approach chart itself. Okay, so if you look through Jefferson documentation, anything that shows those coordinates around the border are WGS-84 based. Now essentially what we could have here is a vector straight to either of these initial approach fixes. You'll see it's where is it? Try and get this to focus. You'll see that point Lima Uniform Yankee Echo Victor is an IAF. It's an initial approach fix. So we can actually get radar vectored straight to that point. At which point we then fly laterally and vertically down this path so that we will break out visually on this particular approach 450 feet above the runway. So if the cloud was at 500 feet, we are flying down without seeing anything, relying purely on GPS and the accuracy of WGS-84, and breaking out visual perfectly in line with the runway. So we've flown for 9 hours, we haven't seen anything, we've made no reference to any ground-based aids, and we've been aligned perfectly with the runway so that when we break out of the cloud, there it is right in front of us. Now that is how accurate WGS-84. It works. We have an accurate model of the globe, and the proof that it works is that aircraft are using it every day to fly precisely under the instrument flight rules and arriving at their runways exactly and perfectly lined up with the runway when they break out of the clouds. Now, show me a flat Earth map that works. You can't even show us a basic flat Earth map that even works, let alone anything remotely close to what we have with WGS-84. And one last point, if you look up FAA Order 8260.58 Alpha, you'll see it shows you the design criteria that is used to design these instrument approaches, okay? And without sort of getting too technical, it is a very technical document because it's got lots and lots of information about how the approaches are designed. But if we just want to look up the term WGS-84, you'll see find WGS-84. You'll see the algorithms and methods are described for calculating geodetic locations, latitude and longitudes on the World Geodetic System of 1984, ellipsoid, for PBN procedure construction. So it's confirming that those approaches are based on WGS-84. If we have a look at Earth, okay, for the purposes of this order, the term R represents the mean radius of the Earth used in spherical calculations and is equal to that many feet. For mathematics, convention and other common equation terms, see order 8260-3. Okay, we won't worry too much about that. So you'll see that if we type in Earth's curvature, or if we type in WGS-84, It's all through the document, okay? 28 times. So the whole document is based on this WGS84. And as I said, you know, it's a very technical document. Probably take me a few hours to go through and just read it fully and comprehend every aspect of it. But it's just confirming that these instrument approaches that we talked about are actually WGS84 based.